It's Friday, March 1st, and this is Season 2, Episode 10 of Mind Body Evolution. I also want to say, if anyone's listening to this, you should check us out at www.mindbodyevolution.info. Josh has some kind of, I think, explosive things to talk about here that are philosophical but also mathematical, and I don't understand it completely. What's going on, Josh?
Well, yeah, I apologize. This is not my field. I can't help myself. This is actually one of the problems with being ADHD. Is not only do I get distracted and look at shiny objects in my head all over the place, but then when I really get excited about one, I can't let go.
I mean, this is also conversations we've been toying with over decades.
Absolutely. So this isn't something that is new to my brain. But in terms of the mind-body evolution, this is something that is there's long-term concepts within humanity of the nature of what the universe is, and that it is all one thing, and that it is a bounded infinite whole. This is a long-term through line from the ancients on down.
A bounded infinite whole, meaning it's not something we can get out of. There's no outside of the universe.
There is no outside, and so I've been thinking about this for a very long time. But recently, when we were talking about this on the show, I've been thinking about it a lot harder. And actually, personally, I think it has to do with the meditation I've been doing. I'm able actually to strengthen my imagination. It's like building a muscle, and that by using visualization, I can build things in my head that can't be seen but in reality. And so I was able to go a little bit further than I'd been thinking in the past, and probably getting closer to what maybe the ancients had been thinking about all of this time. They're trying to describe what a bounded infinity looks like. And so the Renaissance thinker Nicholas Cusanus that I was mentioning last time described the universe described God as a circle whose circumference is equal to its center. And so that is the idea of a bounded infinite, because if you have an infinite circle, then the edge and center is everywhere in that circle. That's what the universe is, but it's a sphere. And so I've been thinking about this a lot, but I was mostly thinking about it from a philosophical point until I realized that there might actually be real mathematical relationships that I could derive from the idea of this bounded infinite. The main problem is, if I'm living in a universe where the universe is only 13.8 billion years old, and let's say I've got stars A, B, and C, and I'm in B in the middle, with A and C on the far sides. If A is 10 billion light years...
Essentially, you're on planet B, and when you look right, you see planet A, and when you look left, you see planet C.
Exactly. And so each one of these things is 10 billion light years away, let's say. Mm-hmm. A distance that I can definitely see.
We can measure and see, yes.
Yeah. We've got great Webb telescopes, et cetera, these days. Hubble could see that far as well. But that means that A and C are 20 billion light years from each other.
That is what it would seem to mean, and I think that's when you look it up on Google, that's what it says.
Yeah, exactly. And so this would have a problem with my concept of a bounded infinite. There would be two problems.
Why? Yeah.
Well, one, it would mean that A and C are 20 billion light years away from each other in a universe that's only 13.8 billion light years old. And so they can't be that far away. Now, one possibility is that the universe is just very, very simple, and A can't see C because it's too far away. It's just it's gone past the beginning of time, and it is outside of time.
But is it? You're saying that it can't be 20 billion light years apart. But if the Big Bang happened and two things are traveling in opposite directions, then one can go 13 billion light years in one direction, and then one can go 13 billion light years in the other direction. So why wouldn't that be 26 billion light years apart?
It is, except it's still inside a universe that's only 13.8 billion light years. So those two galaxies, let's say, which are 26 billion light years apart, they really are that distance. But they can't appear to each other to be that distance because there hasn't been enough time in the universe for them to be that far apart. So even if they really are, I think they really are that distance apart, they would appear some lesser distance. And I came up with a formula to figure out what that apparent lesser distance would be. I realized that there has to be a boundary at 13.8 billion light years. And so I made a very simple boundary equation.
The boundary is because if things are 20 billion light years apart, they wouldn't be able to see each other because we can't see past
it's
13 point.
It's worse than that. They'd be before the beginning of the universe.
Because we'd be seeing past the point where light would let us see because the Big Bang happened at a point that we can theoretically measure.
I have a let's call it faith. It's a lot like a faith in a deity, except it's a faith that the universe is a certain way. And one of these articles of faith is that it only is 13.8 billion light years, in age. It has a particular age. If it came up with a different age, I would be fine with that. But I've accepted the idea that the universe has a beginning and has a particular age. I reject the idea that there are things before the beginning because it's the beginning of time itself. I reject the idea that there's anything outside the universe because that's the universe. And so by definition, everything has to be inside this, let's call it a sphere, but it's not a normal sphere by any means. A sphere that has a boundary in time, 13.8 billion light years, but no boundary in space.
Wow, that is hard.
It's really hard to conceptualize. And so
the reason that there is this discrepancy is there is a boundary in time, but there is no boundary in space. And since time created space, we have a problem.
Well, it's not time created space, but all space occurs within time. And that time is not infinite. Space may be infinite, but time is not infinite. Time has a beginning, and there's nothing before the beginning, and there's nothing outside of the beginning. It's just inside of that. Everything in space began at the same time and is in the same place in the future now from the beginning. So you can't go outside of time.
Yeah.
It just exists. So things that are 20 billion light years away
from each other will then be converted into a distance within 13.8 billion light years in time. So that there is no further they can get away than 13.8 billion light years, but there's still a distance apart from each other that is observable. So what I did is I came up with an equation that would describe things as within normal space, as long as things are less than 13.8 billion light years, everything appears more or less as it should. That the actual distance to something is the same as the observed distance to something. However, as you get closer to the beginning of time... In other words, as you look further and further away and see older and older light...
You get to this boundary. And so I described the boundary as...
And the boundary being the beginning, which we cannot see past.
Right. So I just made a mathematical boundary. And so this is something I'm used to in biology. I made it look a lot like a population growth equation because that's what I know how to do. I don't know advanced physics, math, etc. And I just put a 1 over 13.8 billion light years minus the observed distance. So as the observed distance gets closer to that 13.8 billion, it's going to divide 1. And eventually 1 is going to be over 0.
Which you cannot do.
Which means you have infinity.
Right.
Which is okay as long as you put it at the very beginning of the universe. You can do that. You can put infinity at the beginning of the universe because it's the beginning of the universe. And so I've hidden infinity, 1 over 0, 13.8 billion light years away. So there is no past that. You can't get to it. And at that point, things are infinitely distant. And I also realized that this had to reflect a sphere, a spherical shape. So I didn't just do 1 over a number that's approaching 0. But I then put it to pi to the third. I did pi to the third because pi to the third is describing a sphere and 3 dimensions. And as you get closer to this edge boundary, it's going to go up really, really fast. By making it an exponent, it also makes those small numbers smaller so that in normal space, you never, ever, ever see them. Because if I have 1 over a very small number, or 1 over a very big number,
Right.
say billions, it's now very small.
Inconsequential to, yeah.
And if I do that to pi to the third exponent, it's even smaller. So it doesn't matter for most situations. But here's the interesting thing. Again, terrible at math, had my daughter help me find a graphing program and a way to solve these things. And I put in some different numbers. And so I put 20 in for the actual distance. So I've got these 2 stars that are 20 billion light years away. What is it going to come up with? And it came up with they're going to appear to be 12.8 billion light years away in the equation I came up with. And so you end up with everything being packed in right at the end, very close to the Big Bang, but still observable. 12.8 billion is something we can see. And so there's a couple of really interesting implications of this. And this is why I wanted to talk today. Not about the generalized concept, which is hard to wrap your head around if you're not meditating all the time. By the way, I could not make this equation. The math is terrible. I literally woke up seeing the boundary condition, like just knowing that this had to be it, and then writing it down. I also I graphed it, and I knew that the slope of the graph had to do with pi to the third. So these things were absolutely philosophical concepts that I was struggling to find math to describe. The math implies some weird things. It implies that a galaxy that's 12.8 billion light years away could be 10 billion years old, because
it's not 12.8 billion years old. It's 10 billion years old.
Yes.
Even
Think
though
about
the
that.
light traveled to us over 12.8 billion years.
I think so. It's very hard for me to understand at this point. I have problems with the ages of stars as I go back, because think about it. If I have galaxies A, B, and C, and I can see Galaxy A is only 10 billion light years away, it can only be 10 billion light years old. But from the point of view of Galaxy C, it's 20 billion light years away.
And cannot be seen.
And is therefore observable at a distance of 12.8 billion light years.
Oh, it is visible.
It is visible, but would appear to be slightly older than its actual age. And this would continue on. So there would be a distribution of extra young galaxies right at the edge of the universe that were slightly too young. And it doesn't go to infinity. It wouldn't be an infinite number of all ages, because there's sort of the way this would work, there would be boundaries on how different from the observation things could be. If I want to get to 20, one thing could be, 1 billion light years on one side and 19 billion light years on the other side. But that observed distance would still only get to...
It would have to be less than 13.8.
It would still have to be less than 13.8 billion. And I think there's a way of now deriving the distribution in ages of galaxies. So this is a testable equation. So you could have a predicted ages of galaxies that you would have to see. And then you would have actual observed ages of galaxies, which right at the very beginning would show some extra young galaxies. I have a feeling this is true. I think there are some extra young galaxies.
We need
really
some astronomers and physicists.
So I have a plan. I have a colleague who studies dark matter, and he's going to help me understand this stuff.
Oh, that's exciting.
To a certain extent, I feel a little bit like I did when I was a kid and discovered that there's a pattern to the 9 times table. And no one was particularly excited by this but me. So it might just be something that everyone knows, and they've written it down differently. So the Einstein field equations are very similar to this in a lot of ways, in that they're describing the shape of space-time. I'm describing it, but mine are very simple equations in many ways, or is a very simple equation, and it makes some really interesting predictions. And I think those predictions match reality, but I need to talk to some people who know reality so I can find that out.
Yeah, you're talking to me. I'm just listening. I have no clue.
Well, I mean, you had the best question to this right from the very beginning. That I think is there's sort of 2 major problems with my idea. One is that maybe things are just out of sight. My objection to that would be they're before the beginning of time.
In that case,
but that would
under
be
your thinking, they
Yes.
would have to be before the beginning.
right, because there's a beginning, and you can't be 20 billion light years away without being before the beginning.
Right.
But that would be a very simple way to explain it. We have an infinite universe, and some things are just out of sight because they're before the beginning.
Well, that doesn't sound simple if it's before the beginning, or it could be that they started at the beginning
And they just moved away.
and they just
And
have
we just
moved
can't see them.
away.
Yeah, that would be a very simple way of seeing that. I disagree with that because I don't think there's a universe outside the universe. I think everything has to be contained in it. And so that's why I came up with this equation to describe the boundaries at the edge of this infinite sphere. Some other things happen. Right at 13.8 billion light years, galaxies would be infinitely far away.
Infinitely
or approaching infinite. Yes, and then there's another match with this is as you get to the beginning of time, galaxies start appearing larger and larger.
Is this something that
This is real.
Okay.
So this is real. They get smaller and smaller, like most things do as they get further away, because of just the angle
perspective?
Yeah. Things get smaller as they go further away, and then they get bigger. And there's no way to think about that except as sort of being projected on the outside of a sphere.
Mm-hmm.
And so if something being projected on the outside of the sphere, it becomes bigger and bigger and bigger. Like looking at yourself in a spoon, say.
Mm-hmm.
Your face fills the entire inside of the spoon.
Mm-hmm.
That's what's happening to these galaxies. So this point-like beginning of time is the edge of a wall that is reflecting basically these galaxies that are filling the whole edge of the wall. It's a really weird way to think about it, but this is what I can do in meditation, essentially.
Is this connected to the background microwave?
Yeah, so
radiation?
that is the Big Bang spread over everywhere we can see.
So as we look farther and farther back in time, things get spread out and larger as we get closer to the very beginning until
eventually
everything just circles around us.
There's an infinitely small point that is in every direction, filling everything. It's the edge. That infinitely small point that's the center is also an infinitely large edge. Now, thinking about infinities.
But this goes back to your Renaissance thinking.
Exactly. So if you accept the idea of an infinitely large sphere whose center is equal to its edge, you can start thinking about these sort of curved infinities. There's no curve involved. Everything is straight. And yet it's existing in a sphere. It's a lot like if you were sailing on an ocean, you would just go round and round in a straight line.
Yeah.
And you would never be on a sphere, as far as you could tell. You would just be moving in a straight line. If you were moving through space, there's no curvature. Everything would just be straight.
Yeah.
And it's only time, at the beginning of time, that everything becomes this.
Well, it
sort of
breaks my
bounded
head,
thing.
but if the center is wherever you are, right? I mean, that's what you're
well,
saying.
because everything is equally distant from the beginning of time. Right, we're all the same age.
Or the fact that we exist now doesn't change. Wherever we can't, doesn't matter how fast we can't travel back in time. We can go towards what we see as the most distant thing, but that's in every direction.
It's in every direction, but it's more than that. So my ABC galaxies,
Yeah.
they have a D, E, F, G. So they keep going. So wherever you are in the universe, you're going to be able to see stars around you in the same way wherever you are in the universe.
Yeah.
It doesn't matter where you are. And there needs to be a series of stars going to infinity. A series
For that to work. Yeah.
Because wherever you are, you would see these stars going back to the beginning of time everywhere. Anywhere you are.
Right.
And so you could
The cosmological constant. Everything is the same.
Everything is the same everywhere. So you could just take these bubbles and stack them to infinity so that they're all lined up in a row, starting at the beginning of time, or actually, there'd be no starting and ending of that line.
Right.
That would just be,
right.
it just goes on an infinite in all directions.
Yeah, it's turtles.
So how do I pack this into a sphere? And that's what I used, pi to the third exponent with a 1 over 0. I'm ending up with getting closer and closer to infinity right at the edge, but everything has a particular distance.
Mm-hmm.
No matter how far away it is, it
Mm-hmm.
hasn't reached infinity yet.
Right.
So there always is a distance it can be. at a certain point, as you get closer and closer to the beginning of time, you do hit an observation wall where the energy of the universe itself is so high you can't see through it.
Right. Everything is essentially so hot that it can't.
Light hasn't been freed, etc.
Right.
And this sort of hides all the real problems with my theory.
Is this what they call? Was this expansion? Was that the initial expansion phase where everything was just so hot and expanding?
Yeah. So you're going. So as you look backwards in time, things are redshifted in distance.
Yeah,
as you look out in distance, things are redshifted. You're also looking backwards in time. That redshift gets bigger the further away you go.
It gets more and more elongated.
But it's not a linear process. It is an exponential process.
Oh.
And it starts to approach infinity as you reach it. Just as you'd expect, if those stars are infinitely far away right at the edge, you'd have infinite redshift right at the edge. None of this, here's the weird thing about my theory. None of this needs movement per se. It's a matter of geometry. So just like the galaxies are getting bigger as you see towards the edge, not because they're getting bigger, but because of the geometry of, say, looking in a reflection of the curved spoon. Your face fills the whole curved spoon.
Yeah.
The same thing is happening with distance. The distance is approaching infinity without there being movement as such.
Mm-hmm.
And as distance approaches infinity, it would be stretching space-time itself and therefore redshifting things. And so you would get, I don't know if the entire expansion of the universe is caused by this, but certainly the early seemingly infinite redshift expansion can be explained simply by a geometry of an infinite sphere. And what the geometry of an infinite sphere... Well, it is.
Yeah. It's just one of the things that's almost impossible to contain in your head.
It is. I don't know how you would do, geometry, like we normally do geometry. Like what's the diameter? The diameter is 13.8. What's the surface area? The surface area is infinity.
Infinite, yeah.
Yeah. So how do you end up with an infinite surface area and a diameter of 13.8?
Right, something that is measurable leads to something infinite. That couldn't possibly be, but that's what you're saying.
But the radius is also 13.8.
And light has a constant speed no matter how it's observed.
Exactly.
From where.
Yeah.
It's just these things are
they are true, they're difficult, but they are, you can contemplate them and you can build real structures thinking about them.
Well, that's what Einstein was doing.
And that's what I'm trying to do. Yeah. And so I know I'm really naive and I've come up with a very simple way to talk about it, but I might have figured out something that people aren't seeing other ways.
Well, I mean, this is the way, all brilliant people tell the stories of their past. They're like, if I had talked to anybody, they would have told me I couldn't do it and I wouldn't have done it.
Well, we'll find out. So I just want to mention one more prediction.
Please.
So I have the prediction of the distance, which will give you a prediction of ages of galaxies that is actually observable, and you could compare predicted ages for a standard model and what my model would predict.
Right.
You could compare these two things. There are so many variants in models that I think most of them would cover all of that wiggle room. So I don't know if there's a single answer there, but it's at least theoretically testable. There's another one that has to do with density. I haven't quite figured it out, but as you move away from Earth, you're in an expanding sphere. And any given layer of this sphere, there's more galaxies because you've got a larger surface area to your sphere. And you've got, galaxies just lying on this sphere. So at 1 billion light years, you've got all the galaxies that are 1 billion light years away. Mm-hmm. And that equals a particular number based on the density of average density of galaxies and the shape of a sphere. Mm-hmm. And you keep doing that. And so every time you expand 1 billion light years, you're going to have more galaxies. Mm-hmm. And this is going to happen in a very repeatable way. Except when you get towards the edges, now you're going to have things where there's, you're looking at something that's a sphere that's actually 20 billion light years around, but it only appears 12.8 billion light years around. You're going to have excess galaxies being observed by my theory.
Right, you can't fit them all in.
You can't fit, well, you can. There's a lot of space, and 12.8 isn't that different from 10, let's say.
Okay.
Right? Because it's different, but it's that would be the differences in age. 20 billion light years would give you a sphere of galaxies that's a lot bigger than 12.8 billion.
Yes.
But again, not that much more. As you get towards the beginning, you're going to get to a point where it's that much more. Because at the very beginning, my thing would predict an infinite size sphere and therefore infinite numbers of galaxies. Luckily for my theory, this is contained at the Big Bang, so you can't actually see it.
Right.
I suspect where things get really, really weird in my description is going to happen inside this place you can't observe because light hasn't even escaped matter and matter hasn't become matter and all of these things.
No differentiation yet.
You don't actually get to infinity because it's just a sea of energy that is itself at least theoretically dense in energy. So it's fine to predict infinite galaxies behind this wall of infinity. So anyway, I just wanted to say this stuff for today. I wanted it to be a short talk. I definitely have predictions that are testable and disagree with modern models. I have predictions for ages of galaxies and density of galaxies that are observable, and I have an equation to predict them.
Are you ready to post that equation?
Yeah, I'll post it underneath this talk.
We'll put it on the website again. That's www.mindbodyevolution.info, which is the official website of the podcast. I have to tell you, this conversation has always been on the edges of my ability to contain it in my head, but I find it consistently fascinating, and I love that you are reaching out towards these other areas of mental scholarly exploration.
The dark matter guy, he's a colleague. I'm really excited to chat with him. Dr. Rada, and he. I hope he has an open mind about this because what dark matter is used to do is to explain the cosmological constant.
Yes.
The difference between my observed and actual distances may actually be the cosmological constant. That might be what flattens everything.
What you're getting at.
What I'm getting at, yeah.
I mean,
and so there might not be any dark energy.
I was just going to talk about dark energy because this is the latest thing. Yes. They're feeling that dark energy is...
If we really are accelerating, my stuff doesn't explain it. Rather than just sort of doing steady state, but I can definitely explain expansion at the beginning of the universe. So it's going to be really interesting to talk to someone who really studies this stuff.
Yeah.
To find out what's happening.
I thought
later.
Things accelerating was an accepted reality.
More or less, but there are people who definitely think that starting around 6 billion years ago, the universe started accelerating again. But I'm having a hard time understanding that, seeing it. I haven't seen good data for it. But it's definitely the consensus model right now. Well, and so I want to talk to someone who understands it so I can play my model off of that.
I look forward to having those conversations, and then I look forward to bringing some of these interesting people into this,
I hope so.
podcast.
That'd be great.
All right, excellent. Thank you, Josh. Until next time.
Thank you, Eric.